We're going to be looking at the required practicals for paper 1 today. Anything that is green will be content that you could be assessed on, while content greyed out would not be on your specification. Today we're going to look at 5 required practicals. 4 of these are possibly on all exam papers. Required practical number 2 will just appear on separate science, but I'll point that out when we get to it. The first required practical is around specific heat capacity. Now, as a reminder for a definition for this is the amount of energy that we need to raise the temperature of 1 kilogram of that substance by 1 degree C. And you might be asked to write a method to describe how we can find the specific heat capacity of a substance. That might be a solid metal. It could also be fluids that are possibly in a beaker that have been heated up instead. With this, it does mean that we have this calculation that comes up in our exam, the idea that change in thermal energy is equal to mass times specific heat capacity times by temperature change. With this, when we go to explain how we are going to find the specific heat capacity of an object, we really need to talk about how we're going to find these other values. So, as a reminder, our energy will be measured in joules, mass will be measured in kilograms. Specific heat capacity is joules per kilogram degree C. This unit is coming from the rearranged version of this equation. You'll do joules divided by these two values multiplied together. And for temperature change, we're going to measure this in degrees C. Now, temperature change is where we need to be careful with our description, because to know temperature change, we actually need to record the start temperature, the end temperature, and find the difference between the two. So as a basic outline for equipment, we are going to first of all measure the mass of the material by using a balance. If this is maybe a fluid, what you would do to find the mass of the fluid is you'd add the empty beaker onto the balance, zero it, and then add your fluid to that. So be prepared, that might be a way that the examiner possibly makes this a bit more tricky. But really, if we want to know specific heat capacity, we need to know the mass of that material, critically using a balance to do this. What we'll then do is we'll have a heater that'll be attached to a power pack. And in between, what would be a handy piece of equipment to have in there is a piece of equipment known as a joule meter. So the joule meter will actually count how much energy has gone through to that heater. So as this is on, we'll get a digital count of the amount of energy that's gone into this. So the idea is that we'll also have to have a thermometer and record the start temperature. So we'll have our equipment set up, we'll turn on the power pack, and we will then, after 10 minutes, turn the power pack off. And we're going to take a couple of readings. We will identify how much energy was transferred, and we'll also measure our new temperature. From that, we can then use our equation. We can know that the amount of energy that went in, we know the mass because we've measured it with the balance, and we also know the temperature change because we found our start and end temperature and have subtracted the two. So using this equation, we can now find our specific heat capacity. My advice for structuring a 6-mark method around this is use the equation. You could even write this at the top of your page. So to find specific heat capacity, I will use this equation. And then you almost want a section in your answer around how you're going to find mass, how you'll find temperature change, and how you'll find your change in energy. So to find the mass, we'll measure the mass using a balance. Remember, if that is a fluid, you'll want a beaker or a container on there beforehand that will reset to 0 to find the fluid's mass. For temperature change, we'll have a thermometer to record the start and end temperature, and we'll subtract the two values. And to find the energy supplied, just name your equipment here. You are going to have a joule meter connected to the power supply. Now, to actually heat this object, you'll also need just a bit of detail in there, that you'll have a power pack connected in series with a joule meter and connected to a heater. And that's the device in which we're actually going to heat this substance up. But once we know these values, we then put those into this equation and find our specific heat capacity. Now, if we're thinking about a whole question around this required practical, this might include writing a method, it might include critiquing a method, it might also and most likely include a calculation. But the other thing that they can commonly ask you is that you are probably not going to find the exact specific heat capacity of a material. And there's a common little thing around this, it's the idea that we are unlikely to have all of the energy that's gone into this actually used to heat the block. And so when we do this experiment, more energy normally appears to have gone into this than actually was used. So we are using a higher value for energy than actually was used within this. With this, you might be asked to give some sensible suggestions for how you could reduce this heat loss. So if we've lost some heat and energy because it's been dissipated to the surroundings, it means that the temperature has not risen as high as it should for the energy that was actually transferred to this. As a consequence, your specific heat capacity, if there is an error, will be calculated and determined higher than the actual true value. And if you're asked why that's the case, you need to explain that energy has been transferred and the temperature has not risen as high as it should for the proportion of energy that's actually gone in. To reduce this, you've got a few different things you can do. If this is maybe a block or if it's going to be a liquid, what you can do is wrap insulation around it. So you could, for example, with this metal, wrap an insulating material around it itself. If this were a beaker of maybe oil, you could wrap the beaker within insulation itself. The other thing that you could do if this were a liquid is you could add a lid to it. Also with liquids and beakers, use a polystyrene cup instead because they're really good insulators. Other little things though are you'd want to make sure the heater was fully submerged into the material you're trying to heat. So for example, at the moment, this heater actually has part of it poking out the top of the material. This part will not be heating the block below. In theory, you want this heater further in. For the next practical, it's for separate signs only, and this is now looking at different materials and their effectiveness as insulators, but it can also look at different factors about that material that might affect its insulation properties also. With this, it doesn't really matter which part around insulators you're investigating, you're generally going to start in a similar way. First of all, you're going to need a beaker at a fixed volume at a fixed temperature. And normally a good way of doing this is to boil water and add a fixed volume, like 80 centimetres cubed, to a beaker. Now that water will typically be in the 90s at that point where you've boiled it. To make sure that you've got a really good controlled temperature, what you can then do is wait for that temperature to drop to maybe 85 or 80 and then start your measurements from there. But you want to ensure these all have the same starting temperature. So if you use a starting temperature of 80 degrees C, it allows you a bit of setup time for the rest of the experiment to make sure that your beaker is set up exactly as you want it to then test that material. So the volume of water and the size of the beaker are both control variables. Now there's different ways that you can do this. If we're looking at the effectiveness of materials, you can place one beaker inside a larger one and then stuff the rest of that cavity with the insulated material. Alternatively, you could just wrap a layer around a beaker and fasten it in place with an elastic band. But what we do want is a lid on this to reduce our energy transfers, and we want a thermometer placed through the hole of that lid. Similar to our specific heat capacity, we're now going to record our start temperature and we'll leave this for a fixed period of time. So you might, for example, wait 5, 10, 15, 20 minutes. But after that fixed time period, what you'll then want to do is measure your new temperature. Now here, what will be changing as our independent variable is the type of material. So you could, as a control, have no material at all. You could use like wool, you could use nylon, you could use felt or fleecy materials or that cotton wool. With each of these, you're going to place that material in the gap and basically see, after a fixed time period, what was the temperature drop. So you could also measure this at regular intervals and produce a cooling curve also. When we do this experiment, you've got to consider the measurements that we're taking. So the common issue we're going to have is that your measurements around temperature may not be particularly precise. One thing to consider, and a key word that tends to come up somewhere in your paper, is this idea of resolution. Now, this is the smallest change a device can detect. So as a general definition, this is what we'd want to say. If we've got a higher resolution piece of equipment, what we are going to get is a far more precise reading. So notice here, this thermometer only measures to the nearest 2 degrees. So these are each of the markings that we see on this thermometer. While this digital thermometer now gives a reading to the nearest 0.01 degrees C. This will measure much smaller changes in temperature. Now, if we have a higher resolution, a benefit of this is we decrease our uncertainty. So here, it does mean if we take a reading, we could be a whole degree out. So our uncertainty is your resolution divided by 2. So here, our uncertainty is plus or minus 1 degree C. While in this one, our uncertainty now is plus or minus 0.005 degrees C. Another issue with temperature is if you're using a thermometer that's like a little stick one, you can get a parallax error occur. So if we view this from above or below, we can read the values to be less or more than they should actually be. So if we read from above, we'll read the value of higher than it actually should be. And if we read it below, we'll read it off as less. What we need to do here is read this dead on. Now this is an example of a random human error. And it's random because sometimes you could be looking from above, sometimes from below. And even if you did look directly from above each time, it probably won't be by the same amount. So your values will be different amounts out each time. So parallax error is a random error that's caused by not taking a measurement at eye level. And it's a common example of a random error that can occur in any experiment where you're having to read off thermometers or reading off rulers. A way of avoiding this is you could instead choose to use a digital thermometer that as a benefit will give a higher resolution, but would also remove this issue of a parallax error. Now, when looking at our effectiveness of different materials as thermal insulators, our independent variable here will be a type of material. And I advise, if you're writing a method, to specify that you'll use 5 different materials, one of which could just include air. Our dependent variable here can be either the time it takes for a temperature to fall 20 degrees in temperature, or you could say that it's the temperature after 10 minutes. Now the bit in bold you could change. We're either looking for how long it took to fall a certain temperature, or you could look at what the temperature was after a certain time. And you can pick there which your preference would be. For control variables though, everything else needs to be kept the same. So the thickness of that material, the start temperature, the volume of that water in the beaker, and the surface area of the beaker are all going to be critical control variables that we require. Remember as well, wherever you can, to name the equipment you'll use. As an alternative to this, you might be asked how we can investigate different factors that affect the thermal insulation properties of a material. So rather than now just how different materials affect this, but what about that material could affect its insulating abilities? So here, for example, we might look at thickness. A common one that we do is we can wrap around one layer of the material, fix it with an elastic band, and then 2, and then 3, and so on. Our dependent variable is exactly the same. We can either measure how much the temperature has fallen by after a fixed time, or we can time how long it takes to fall a fixed temperature. As long as you do the same thing each time, that's fine. Now, with thickness of material, it should mean that the colour of that material, the start temperature, the volume of the water in the beaker, or even that surface area of the beaker should be kept the same. What we could do is actually swap thickness for another one of these variables and investigate that instead. So if we wanted to investigate beyond just thickness, for 2 marks, we'd identify, right, we'll control thickness, but we'll now vary maybe the colour of the material. Moving on to required practical 3. This is now for everyone and can be on combined science and on higher. And really within this, we tend to see that a lot of the experiments and practicals around electricity be prepared to draw circuit diagrams or be prepared to interpret the results also. But typically, if we're investigating anything around electricity, the circuit tends to look like this. We've got a power supply or a battery with an ammeter in series, a voltmeter across whatever we're testing, and a variable resistor also in series. So if we want to look at how maybe length of wire affects resistance, we'll set our diagram up as shown like this. Details to include here is that you would have the ammeter in series, the voltmeter in parallel. And if we're looking at length of wire, we'd start with like 10 centimetres, have crocodile clips that we've measured this with a ruler 10 centimetres apart. And we'll record our current and voltage. And we can then use the formula for resistance to find the resistance overall. Now here are independent variables the length of wire, so it'll be important here to test at least 5 different lengths. So I'd advise 5, 10, 15, 20, 25, or 10, 20, 30, 40, 50. 5 values, fixed distances apart. What you can then do is plot even a graph of resistance against length. In this investigation then, our independent variable now is the length of wire. Our dependent variable is the resistance, but when you're giving detail around this, you need to mention what you're going to be measuring. So current with an ammeter in series, a potential difference measured with a voltmeter in parallel, and how you'd use these. So that idea of resistance, we'd use V equals IR, the equation for this, to figure out resistance. If we're going to change the length of wire, everything else about that length of wire needs to be kept the same. So this includes the material of the wire, maybe nichrome or copper, includes the thickness of the wire. Thicker wires tend to have lower resistance than thinner ones. But also how the components are arranged. Are they in series? Are they in parallel? But finally, we'd also need to control the temperature of the wire. If we wanted to investigate this further, if we've tested maybe length of wire, you could then control this and maybe investigate the material or thickness instead. But for here, you'd simply swap your independent into controls and controls into interdependent. One common theme though that comes out of this practical is about the importance of controlling temperature. The rule here is that high currents will tend to cause an increase in temperature of wires. And if wires increase in temperature, their resistance increases. So it's really important that in this investigation, we control current. Because if we can control current, we can control temperature, which means we don't have something else affecting the resistance. So what we need to do is make sure that we're reducing this. Now, as background behind this, higher temperatures cause the metal ions within that wire to vibrate more, making it more difficult for electrons to move past, causing that resistance to go up. To control this, a couple of things you can do. Turn the power pack off in between readings. When you're ready for your next reading, then turn it back on. That will cause a break in the circuit, just allowing that temperature to reduce a little bit. But the other thing is it's really important to have a variable resistor in the circuit, because every time we change the length, we'll notice the current changes. If we adjust the variable resistor to return current to the same value, what that will do is ensure that the temperature that current causes is controlled. So a nice way of controlling temperature is to keep our current low and to adjust this variable resistor every time we change this length of wire to ensure that if we keep current the same, in theory we should be keeping temperature the same. The next practical looks at IV characteristics for different components. Now, as a quick summary, we'll find different kind of features depending on the component itself. Ohmic conductors will tend to show a directly proportional relationship. A filament lamp has got this curve, while a diode is used in circuits because it only allows current to flow when in one direction. So here we've got our ohmic conductor. This idea of a directly proportional relationship, we can tell is directly proportional for two reasons: constant gradient, and it's going through the origin. Now for this one, what this basically shows is that as we increase potential difference, current also increases, but resistance must be staying the same. With our filament lamp, what we now see is that as we have an increased current potential difference, the resistance changes, and so this causes now what is no longer a directly proportional relationship. The resistance is changing, and so we no longer see that constant gradient. With a diode, because it only allows current to flow in one direction, what we find is that when the potential difference is reversed, there is no current. For Required Practical 4, we might be asked how we can investigate the IV characteristics of a certain component. So for example, maybe a resistor. Now for this, notice our setup with the diagram is very, very similar to earlier on. We have a current placed in the circuit, measured using an ammeter, and this is in series, while the potential difference is measured through a voltmeter, and that's now in parallel. We still have that variable resistor also, but now for a slightly different reason. So if we want to investigate the IV characteristics of a resistor, what we'll do is set up our experiment as shown. Details here, if you haven't drawn the diagram, is to mention that series will be the ammeter while the voltmeter will go in parallel. We will then set it up, record our current and voltage, and then we'll adjust that variable resistor 4 more times. And as we do, we'll record our new current and our new voltage. So you might try and adjust this to read off a current of like 1, 2, 3, 4, 5 ohms or 5 amps. We'll then swap the leads on the battery so that actually then everything becomes negative, and we'll repeat this again. So we'll then take 5 more readings, adjusting that variable resistor as we go. For the last practical, you might and do need to be prepared to talk about how you can determine the density of different shaped objects. This might be regular shaped, it might be an irregular shaped object. Now for either of them, you're going to need to measure your mass of the object using a balance. If this is an irregularly shaped object, it might even be worth, for extra credit, talking about the fact you need to measure the mass first. Because if you're about to submerge this in water, you don't want its mass to be increased because it's a little bit wet. But for a cube, we'll just measure its mass using a balance. Because it's a regularly shaped object, we'll now measure the length, width and height and multiply those together and find our volume. And once we know this, we can use the equation density equals mass divided by volume to actually find the density of this object. Now when writing the practical for this, similar to specific heat capacity, I would recommend writing your equation at the top. I will use this equation, and then give detail by each of your measurements. So talk about how you'll find your volume, how you'll find your mass, being really particular to make sure you've named your piece of equipment. So we'll measure the length, height and width of the object, and in this case, multiply those values together. Mass, we'll reset it to 0, add the object and measure the new mass. And then we'll use this in this equation. If the object is now an irregularly shaped object, this is where you've got a couple of different methods that you can use. If we're using displacement beaker, sometimes called the Eureka can, we'll fill so that the water level is just below the spout, and they will want to see that detail. And we'll have an empty beaker below that spout ready to catch and collect any displaced water. We'll add the item to the beaker so that it's fully submerged below that water level, and we'll collect the displaced water. And we'll measure this. In theory, this volume of water will be the same volume as the object that you've placed into that beaker. Your alternative method is you can half fill a measuring cylinder with water, record the start volume, add your object, measure a new volume, and find the difference between the two. Both of these will give you your volume. Once you know that, you know your mass, you know your volume, you can find density. Remember, for the mass, the extra bit of detail that you can give is to suggest that we weigh it first before adding it into any water, because when it comes out wet, it'll be a little bit heavier than it should otherwise be. We'll use those values to find our density overall. Be prepared again for discussions around errors here. So there are random errors and also zero. Every time we use a piece of equipment, there is a chance that an error could occur. Now, both measuring volumes and lengths introduces this random error of parallax error again, while a zero error is when you've got a piece of equipment that hasn't been reset to zero properly and is a systematic error that's applied to every single result that you take until you realise and correct it. If you do identify at the end of your result taking you've got a zero error, you need to actually identify the value of your zero error and then just subtract it away from all the results that you've taken. Parallax error that we covered earlier is when we don't take a measurement at eye level. If you read it from below, you normally read the value off as too small. If you read it from above, you read the value off as too high. The best thing to do here in the best practice is to read at eye level, and we look, especially for water levels, at the lowest point of that water level. This is a random error because actually you're not going to be reading exactly the same height each time.